So we did a modified version of Jonathan Gutow's lab published in the Journal of Chemical Education titled Halide Quenching of Quinine Sulfate Fluorescence, a Time-Resolved Fluorescence Experiment for Physical Chemistry. And what we were trying to measure was the effect of chloride ion concentration as a quencher for the fluorescence of quinine sulfate. So what happens in fluorescence is you have molecules in their ground state, and they get excited by a light source to an excited state, and we call light at some excitation energy. And then as those electrons come back down to the ground vibrational state, they emit a photon. But you'll notice that those electrons are coming down to the ground vibrational state and not the ground state. So there is a difference in energy between the excitation energy and the energy of the emitted photons. And so what we wanted to do was measure how long those electrons stay at the excited state before they come back down, which is basically we wanted to measure the difference in the time if you took a stopwatch and pressed start when you emitted the exciting photon, when you pulsed the laser source, and measure how long it took for after the excited photons were emitted for the emitted photons to come back out. So we used an instrument similar to this one, but I would say more similar to this one to do that, where you have your light source, you have your, which I think we had a laser, you have a monochromator selecting for a particular wavelength, you have your sample here, and then you're measuring the fluorescence perpendicular to the sample through another monochromator, and then you have a photomultiplier tube, a PMT, that is going to count the emitted photons. So again, what we're trying to measure is the lifetime of the fluorescence. So we start the clock, say you start the clock when this photon is emitted, and then you stop the clock when the emitted photon comes through the detector. And that's called the fluorescence lifetime. So we got charts that look like this, and as you can see, that lifetime happens on the nanosecond time scale. And so what happens is, say this is when the photon gets emitted from the light source, and you can see there's about a 20-second time delay between when the clock starts and when the photons are emitted. And then every point here, the instrument integrates the time, and you can see here it integrated the time over 20 seconds, so it said, okay, we have X number of photons coming back through the detector after 20 nanoseconds, after 40 nanoseconds, after 60 nanoseconds, etc. And as you can see, most photons are coming back through the detector, are getting emitted through the detector after about 10 nanoseconds. And so we made up 6 different solutions with 0, 0.02, 0.03, 0.04, 0.06, and 0.08 molar chloride ion concentrations, and we observed the lifetime in nanoseconds of the fluorescence. As you can see, fluorescence lifetime decreased with increasing chloride concentration. So what does that tell us? That tells us that we have dynamic quenching as opposed to static quenching. Why? Well, static quenching is when the quencher forms a complex with the fluorescing compound before it gets excited, before it gets up to the excited state at all. So if static quenching was the case, we would have very few molecules getting to that excited state. In dynamic quenching, what happens is the chloride ions or the quenching ions are going to collide with the excited electrons, with the excited molecules, and force them to come back down to the ground state more quickly than if there was a quench. So as you can see, we have a very linear relationship with chloride ion concentration on the x-axis and the decay rate on the y-axis, and that's measured in inverse microseconds. And so we have a r² value on this of 0.9976, which is pretty good. So we have some questions to answer about this data. The first question that we needed to answer was, what is the value of KQ? Well, KQ is corresponding to this value, which is the slope of the line, and I have those calculations right here. So we have the value of KQ is 4.3 plus or minus 0.02 times 10 to the 9th inverse molar seconds. The theoretical value from the Gutau paper is 5.8 to 6.5, so we are on the same order of magnitude, but still kind of considerably off. And what does this value refer to? Well, it refers to the value of the KQ right here. It is the collisional deactivation rate constant, which basically describes the effect that the quenching concentration has on the decay rate. The next question we want to answer is compare and contrast the two fluorescence methods used in this lab, scans versus lifetime. So this is the lifetime method of measuring fluorescence. We also did an absorbance spectrum of it, and this is the picture obtained. And this is really poor quality, but this peak is at 317 nanometers, and this peak is at 347 nanometers. So we have nanometers wavelength on the x-axis and intensities on the y-axis. And as you can see, it's pretty qualitative. There's not much we can conclude from this. So calculating the lifetimes allows us to calculate the lifetimes on the nanosecond timescale, which is just something we would not be able to do if we were doing purely absorbance calculations. How could this instrument be used to analyze two different compounds with similar emission and excitation spectra, but very different fluorescence lifetimes? Well, if we had two compounds available in this sample, we would have a histogram like this, but we would have two peaks. We would have one peak for one molecule, say the quinine sulfate, and then we'd have another peak for the second molecule that would have fluorescence lifetimes on a different time scale. Why is it possible to use a 310 nanometer pulse diode to excite the sample when the maximum excitation wavelength is 350 nanometers? That's because the emitted photons are of a different energy than the exciting photons. So we're coming in with energy from the ground state to the excited state, which is more energy than coming from the excited state back down to the ground, to the excited vibrational state. And so because the because we have a difference in energy there, it's possible to use a 310 nanometer pulse diode to excite the sample when the maximum excitation wavelength is 350 nanometers. How would the results of this experiment change if we ran this experiment at 5 degrees Celsius? Well, at 5 degrees Celsius, at lower temperatures, we would have fewer collisions. And so if there were fewer collisions, the effect of the quencher would be a lot less significant. The relationship would be, but you might have to add like 2 or 3 times as much chloride ions in order to have the same, in order to get to a 2.5 second lifetime. What do the absorbance spectra of the unquenched and quenched quinine samples show in terms of chloride ion concentration? I think that really just shows that I'm not sure if we did actually ended up doing an absorbance spectra of the quenched quinine samples, but I think what would have happened if we did do that was that the quenched quinine sulfate samples would have a different absorbance than the unquenched samples, and so we could tell that it was quenched versus being unquenched because there would be a shift in absorbance, but we would be unable to tell we would be unable to tell the exact relationship between quenching and fluorescence and understand that at the nanosecond timescale. And so that's all for that lab. Sorry for the poor quality of the picture. Hope you enjoyed it.